So to continue the story of greenhouse gases and greenhouse effect, we obviously have to look at the molecular structure, which I already mentioned: symmetric molecules, asymmetric molecules. We have already seen that water vapor has this 105-degree bend because of the what do you call it, attraction versus repulsion by the free pair of valence molecule electrons on the oxygen that is attaching to two hydrogen atoms, right? You know what that is. So water vapor is indeed the most important greenhouse gas. 66 to 85% of the greenhouse effect is related to water vapor, but the most critical thing to remember is that this is a feedback gas, which means if you warm the atmosphere, water vapor will increase, and that water vapor is a greenhouse gas, then it can have a positive feedback, as we saw in the definition of the feedbacks. But water vapor can also condense and form clouds, and if the clouds are reflective, as we saw in the radiation balance, then they can actually counteract the warming. So water vapor plays a mixed role, plus water vapor only has a short residence time. So its concentration with altitude and with latitude varies a lot, because air temperature vary a lot with height from the surface and away from the tropics. Things to remember. Carbon dioxide is a natural part of the atmosphere, has a very important role to play to maintain the global mean temperature at 15 degrees centigrade, and it's the greatest relative contribution from human activity. So in terms of the contribution by humans to trapping more energy by burning fossil fuels and deforestation and other things, it's mostly coming from increases in CO2. But we have also been good at increasing methane from coal burning, from there are natural sources like wetlands and cattle and so on, and it also turns out to be related to economic activities. And methane is also emitted from landfill decomposition, so things that rot. Humans produce a lot of waste, as we saw before. And it also comes from huge amounts of water that are stagnating behind these huge dams. When you build big dams and there is phytoplankton bloom and anaerobic respiration and so on, methane gets produced as well. Okay. Other trace gases: nitrous oxide, chlorofluorocarbons, and ozone, which we already mentioned. So here is fraction of the contribution. This is already old. We are now at 415. So almost 55%, 56% is coming from CO2, ozone, halocarbons, which are CFCs. We replace CFC with HFC. HFC turns out to be even worse for the greenhouse effect. Remember, CFC was banned because it was causing ozone loss, which is bad for life. But now we have CFCs which are bad for greenhouse effect. So we can never do anything right, can we? Anyway, methane is a small fraction as well. So here are the molecular structures: dichloro, difluoro, methane. I think this is CFC11, I suspect, and this is CFC12, I think. Chlorofluoro or trichlorofluoroethane or some such thing. So these are asymmetric molecules, can allow short wave to come in and get excited by the outgoing long wave, and it's the kinetic energy of the molecule that is a measure of the temperature, right? So their energy increases means their temperature increases, and their OLR coming down increases, as well as OLR going out, but OLR going out is not increasing as fast as the OLR that is getting trapped because of these greenhouse gases. H2O, obviously asymmetric. N2O is not a greenhouse gas, perfectly symmetric. O2 as well. Sorry, N2O is not symmetric. N2 is symmetric, not N2O. N2O is asymmetric, as you can see, two N's and one O. Carbon dioxide, as I said, is symmetric, but it has this bending mode which makes it sensitive to various bands of infrared radiation. Methane is obviously asymmetric, and so on. Water vapor, more complicated story than we imagine, and this is the low-level specific humidity measured in grams of water vapor per cubic meter of moist air. I suspect this is averaged over the water column, but nonetheless, as I said, warm waters in the tropics and low latitudes have high amounts of water vapor because air gets heated, rises, picks up evaporated moisture from the ocean, brings it into the atmosphere, where there is the Pacific cold tongue. Remember upwelling, cold SSDs, so low water vapor. So obviously the dependence of water vapor on temperature is exponential. Hence, small changes in temperature change the amount of water vapor by exponentially. So warm temperatures here, warm temperatures over land here in the Amazon, cold temperatures here, and so on and so forth. And as you go to higher latitudes, obviously temperatures drop off and you get into polar regions which are very cold. So obviously those regions have very small amounts of water vapor. When we come back to the ice albedo feedback, one of the most important feedbacks in the system, this aspect of temperature dependence of water vapor in the atmosphere becomes very critical. Why? Because at high latitudes, where we tend to build glaciers, and other than the high mountains, where also temperature gets cold, snow is needed to build glaciers. But if temperatures are cold, water vapor is very low, then snowfall rates also will be very low, which means building a glacier will be very slow. Water vapor low, snowfall low, glacier building slow. I just rhymed it right there in front of you. Okay, so here is the vertical distribution, again looking at kind of a zonal mean meridional section going from 90 south to 90 north. Remember the Hadley cell we looked at, and so on, with zonal mean meridional sections. So water vapor is obviously high near the surface, drops off as you go to high altitudes, and then drops off towards the high latitude. So water vapor is a feedback gas. This is the aerosol map. You can see the forest fires burning in California, setting plumes of smoke, which includes unburnt carbon monoxide, carbon dioxide, sulfur, sulfuric acid, ozone, and so on. Okay, and these are emerging from the ocean. So you can see hurricanes like Harvey here going off, which is obviously carrying water vapor signature, and oceans produce huge amounts of sea salt, and there is massive amounts of dust plumes coming from Sahara Desert. Sahara is desert. Strong trade winds can lift dust high into the atmosphere, and you can see that dust, even bacteria from the Sahara, make it all the way over into the Western Hemisphere. Long distance transports, once they're lifted into the upper atmosphere, if the air is dry, as it is in the subtropical regions, it can be carried long distances. For example, pollution from China makes it all the way into US, and smoke from California fires has not only made it to the East Coast, but all the way into Europe as well. Sea salt is picked up by turbulence at the surface. Tons and tons of sea salt is thrown into the atmosphere. This is why if you live near the coast, everything can get corroded. Cars, if you allow the air to come into your house, pots and pans can even get corroded, and so on. So aerosols have an impact on the greenhouse effect depending on whether they are scattering or absorbing. but sea salt also acts as cloud condensation nuclei. The aerosols also tend to affect clouds, brightness of the clouds, cloud droplet sizes, so amount of rainfall. They also affect hurricanes and so on. So I'll stop this here to give you a good sense of the greenhouse molecules and their impact, and then I will go into the global warming potential of each of these greenhouse gases. Okay, that's an important thing.